5, 4, 3, 2, 1, 0. All engine running. Liftoff. We have a liftoff.
Nuclear fusion propulsion. Do I have your attention? Probably. After all, we need to get to places like Mars and beyond Mars faster than on the current chemical rockets. There are actually some startups working on nuclear fusion propulsion, and one of them, Princeton Satellite Systems, our guest this week. Enjoy.
My name is Raphael, and I'm an investor and advisor to space companies. Just as a reminder, this podcast is for informational purposes only, and nothing should be taken as investment advice. This podcast is sponsored by Nano Avionics, a satellite manufacturer and mission integrator. Their technologies enable many space companies worldwide to offer services that improve life right here on Earth, such as providing global connectivity, conducting Earth observation, or contributing to scientific discoveries. Check them out, and also check out my episode with the CEO and co-founder. Sadly, I am not a rocket scientist, but I'm an alumnus of the International Space University. ISU offers a number of educational programs about space worldwide. Check them out at isunet.edu. And just some final things before we start the episode about ourselves. If you enjoy the podcast, please leave us a 5-star rating on your favorite podcast platforms such as Apple or Spotify. If you want us help expand our work, you can do so and support us at www.patreon.com/Space Business Podcast, and we'll also put that link in the episode notes. And lastly, you can follow us on Twitter at podcast_space. Hey, space enthusiasts, time for another episode. Very exciting episode today. We're going to talk about a very advanced form of propulsion, as we will hear about. And my guests today are Michael Palushak and Chris Callejo from Princeton Satellite Systems. Thank you.
Thank you. Thank you.
Guys, do you want to, one of you can just give us the elevator pitch on what you guys are doing?
Sure. We started Princeton Satellite Systems in 1992, and the goal was to develop guidance, navigation, control, and propulsion systems for spacecraft. So we've done a lot of the work. A lot of our systems are flying now. We've worked with companies all over the world, including the Swedish Space Corporation. And our area that we're pursuing most heavily is space power and propulsion. And we have two major projects in this area. One is we're developing a Brayton cycle heat engine, which would be an auxiliary power system for spacecraft that would use whatever fuel is on board the spacecraft, burn it, produce electric power if you needed boost power for your satellite. The other, which is a little bit further off, is a fusion power and propulsion system based on the Princeton Plasma Physics Lab, PFRC. That's a Princeton field reverse configuration. It's a unique geometry that is a driven system, so it doesn't heat itself. It uses radio frequency power to heat it, and it allows for both power and propulsion in the same package. And because it has a very low neutron flux, it has a potential for low life and can pretty much be built with current technologies. No new materials need to be invented. Chris can tell you a little bit more about that since he's our lead experimenter on that program.
If I can jump in, how did you, so nuclear fusion propulsion, yes, you mentioned it was a bit further off, but indeed it sounds, very futuristic. I think that's literally what's featured in some of the prominent science fiction works, novels, movies. I think for example, in the 3-body problem, that's what the spacecraft are using is basically fusion drives. But how did you guys decide to do this?
Well, in 1999, Sam Cohen of the Plasma Physics Lab and I wrote a paper on the future of space propulsion, saying that essentially we had to go to forms of plasma propulsion to get the higher exhaust velocity to allow you to do really ambitious missions, like going to the outer planets with big payloads, interstellar missions, and so on. Sometime after that, he started working on the Princeton field reverse configuration, which is a potential fusion reactor technology, both for the ground and for space, which is very small. So by the nature of the machine, it would produce 1 to 10 megawatt electric or terrestrial application. And this is sort of ideal for space because it's about the size you need for most robotic missions. You need maybe more like 100 to 200 megawatt electric for a human Mars mission, but it seemed to be an ideal system for space applications. So we started working with them. We submitted a proposal to NASA for then under the NIAC program. That's for really advanced things. And Stephanie Thomas, who was unfortunately couldn't make this podcast, it was the PI on that. And that was very successful. And that we followed it up with an ARPA-E grant to actually do more plasma physics experiments, which Chris continues to work on.
Okay. And so since we are a non-technical podcast, we probably have to take a step back and explain a little bit. So I think probably to the extent people are familiar with nuclear fusion, people who are listening to us, and unless they happen to really work in this field, it's sort of the stuff you sometimes hear in the press, right? So like, there's this huge project and it's basically about terrestrial fusion for power generation, right? Which is, I'm going to assume, is obviously different, right? But there are some people who are familiar with the huge project we have in Europe, the ITER or ITER thing in France, and probably a lot of our listeners have heard the news last year from the National Ignition Facility. And maybe if you can kind of just take that step back and sort of, for a non-technical audience, sort of explain sort of like what's going on in fusion and sort of like what you guys are doing in layman's terms, how that fits in so people can mentally place it.
Sure. I actually visited ITER last year. It's an incredible experimental facility, gigantic. So you can think that there are kind of generally two branches in fusion. One is inertial confinement, which is like laser fusion, and the other one is magnetic confinement, which is what we're working on. Now, there are lots and lots of different types of machines. ITER is a tokamak, and the nature of that machine is it has to be huge to work. And that's because of the ratio of magnetic pressure to plasma pressure. So it's very low. So you need a big machine for it to work. So an ITER type fusion reactor, which would be suitable for ground applications, would be gigawatts, much like a gigantic coal plant or maybe even bigger than most natural gas plants now. There are other magnetic confinement concepts, for example, stellarators, which use really twisty magnetic fields to confine the plasma. They have some advantages. And there's work being done in Germany and other places on it. There are actually two spin-offs from Plasma Physics Lab working on that. That'd also be a fairly large machine. Now, our colleagues at Commonwealth Fusion are trying to use higher magnetic fields to be able to build a more compact tokamak. That's also work being done at Tokamak Energy in the United Kingdom. So those are bigger machines. A company called TAE is trying to do what's called boron-proton fusion. The advantage of that is aneutronic. And I should mention there's sort of two broad classes of fuel. One is fuel where most of the energy is in neutrons, like a deuterium-tritium reaction. The other one is aneutronic, like deuterium-helium-3, which we use, and Helion, another company that we know about, is using. And then there's boron-proton, which is really aneutronic. The challenges of the aneutronic fuels is they need much higher plasma temperatures. So, and there are many, many different types of geometry. The University of Wisconsin, University of Maryland, they're working on mirror machines, really interesting work. So there are all these different magnetic geometries. Our geometry is called the field reverse configuration, which essentially you have a closed torus, magnetic torus. Fields close the fuel into a form where you can heat it. And we heat it only with radio frequency, like an induction motor. So what we end up with is a very compact machine, something like ITER. In fact, the big fusion machines really want to use what's called electron cyclotron resonant heating, where they heat the electrons. That requires hundreds of gigahertz RF frequency. Ours is more like in the megahertz range, which is easier to do with power electronics. So you can imagine almost any magnetic configuration, and there will be a fusion machine related to it. So the advantage of our approach is that it's small. And in fact, the nature of it means it can't be much bigger than 10 megawatts for a variety of reasons. And that's why it lends itself to space propulsion or modular or mobile application on the ground. For example, if you needed an emergency generation after a hurricane, you could then use this. You could bring this in on a truck. So it's kind of a different business model. It also could be used for modular plants. Now, one of the challenges with our technology is we're using deuterium helium-3. And as some of your listeners may know, there's not a lot of helium-3 around.
Yes.
It turns out, right, but it turns out there's enough in natural gas production. Currently, it's not collected for about, 1.5 gigawatts of power production a year. So it's not a small business, but it's a high value business. So if you as an investor said, well, I want to invest in something that's going to produce, that's going to replace, a third or half of the world's power generation, you'd be looking more for the DT machines, deuterium tritium machines. But if you're looking for things like, for example, powering villages or towns in Alaska, mining operations, space operations, our technology has a lot to offer.
And you did mention that your technology was, so you mentioned the two broad categories of fusion, right? Inertial confinement and then magnetic.
Yes.
And I think you said you guys are on the magnetic end. So again, I'm going to ask a lot of stupid questions here, right? Because I'm not an expert. But so when I hear magnetic fusion, then I go back and think of the ITER reactor. But generally when I think of magnetic fields and magnetic confinement, right, I think of like huge magnets and heavy magnets. And then
Yes.
the space person and me were like, well, that's not good. Like, because taking heavy stuff to space, I mean, that may all change next week if Starship flies successfully, but sort of the general view is that, taking a lot of mass into space obviously is not good, right? You typically want to reduce mass.
Right.
That's absolutely true.
Yeah.
And we've actually done mass budgets for this. And we think, and this is with off-the-shelf low-temperature superconducting magnets, that we can get a specific power of a kilowatt per kilogram. So that's lends itself to most space missions. Basically, you could take a mission that was going to go to Pluto, go into orbit around it, and take 1,000 kilograms to Pluto, a big payload, a lot of power, and you can launch it on an Atlas. So it's not a big machine. That's the advantage of this technology, is that it is small and compact. You're absolutely right. If you want to put a tokamak in space, you're definitely going to go with SpaceX's Starship, because you're going to need several of them to put everything in space. Absolutely.
So some intuition behind why we can think of this smaller, compact type of machine instead of what you had this intuition about a tokamak being large. Has to do with partially the field reverse configuration. It's a different type of magnetic field geometry, and it uses something called self-organization. It's a fancy plasma physics term to say that instead of having to route the plasma through these huge magnets in a donut type of formation, and then you also have huge magnets that are around the whole donut that are called colloidal field magnets. In this case, of the field reverse configuration, you just have a cylindrical vessel with magnets around that. So it's a nice linear vessel. And you spin up the plasma in some way. We do radio frequency heating. TAE, which is another company, does neutral beams. They send in beams of neutrals. And if you spin up the plasma, it can create its own magnetic field and actually confine itself in the background magnetic field. It actually creates a magnetic field that reverses against the background and makes like a magnetic bubble, in a sense. So it's almost like a mini scrunched down tokamak in terms of its fields, its magnetic fields. And so you don't need to worry about these huge central magnets and then putting shielding between the central magnets and the plasma, and then having the plasma, right? You're condensing down a lot of space with a field reverse configuration. Of course, there's some more interesting plasma physics that you have to consider in working with a field reverse configuration, but there's some really great benefits there as well.
And this setup, sorry, what's it called again exactly? The reverse?
Field reverse configuration, FRC.
Okay, the field reverse configuration. So is it a mathematical concept for now, or has it actually been done on Earth?
It has been done. Actually, the first instances of the field reverse configuration were in the late 50s or early 60s. It was discovered by accident, actually. And the name comes from them reversing the field of something called a Z-pinch. And you can think of it as a very intense current down the line almost. Actually, sorry, it was a theta pinch. I'll clarify that. So they reversed the current for a theta pinch. And you can look that up online. That's another type of plasma experiment. And when they reversed this field, it actually seemed to be very stable for some time. And it made this kind of closed magnetic bubble. And people were trying to figure out what happened. So since then, people have experimented with various types of generation mechanisms of how to generate this type of closed magnetic bubble. Then the one that I mentioned, the original one, was to take these huge currents in the magnets and then flip them negative very quickly, right? So to send a huge amount of current through these magnets and flip them. But then people started to experiment with radio frequencies, and which is what became a bit of the seed for Sam Cohen's invention and what we're working on, the radio frequency method. And then there's also the aspects of, the method of neutral beams that I mentioned that TAE uses, where you send in big beams of neutrals and they hit it's like kind of like spinning up a bicycle wheel, right? You kind of push it on the top and on the bottom in opposite directions, so you spin it up, right? So that's another way that people have pursued these, and there's been slowly accumulating research over time. But yes, that's kind of the origins of that. Oh yeah, I was going to also mention that another reason why our FRC in particular ends up being even smaller than other FRCs is that in the case of, let's say, neutral beams require a certain length to penetrate enough to give their energy to that bicycle wheel to spin it up, right? And so if you make it too small, not enough of the neutrals will actually hit into the plasma or actually deposit their energy. So this goes with some of our the innovation of the PFRC, the Princeton field reverse configuration, that it uses this radio frequency heating method that penetrates the plasma and can heat up a small enough plasma, something that's more, let's say a 0.25 meter radius or something like that.
Okay, and then so we already discussed the mass budget, kind of coming back to space and on mass. Michael, you mentioned the example of that even a system that can take a sizable payload to Pluto could fit inside an Atlas. How does it look on the power budget, right? Because you do need this initial energy to as Chris called it, spin up the plasma, right? And I guess another question is it like a one-time initial spin up and then it's self-sustaining, or do you have to keep putting power into it? Which I guess then kind of triggers a further question, which is sort of like the people who are vaguely familiar with, sort of the news stories about fusion on Earth, right? They keep on hearing all of this, the stuff about a net positive being thrown around, right? And sort of like, is your system net positive? Does it have to be net positive? If you can basically talk about the power budget and the energy side of things.
Our system is fully self-sustaining. So what happens is we get the fusion reaction. The products of it, in our case, actually are X-rays and high energy particles. All of that is converted into either thrust or electric power. The electric power is recycled back to drive the reaction. So it's a driven machine. So in other words, the products do not transfer their heat directly. That's used for thrust or to sustaining the fusion. So we get an overall total system gain. This would be on the ground, you call it wall plug gain of about 2 or 3. So in terms of startup, that's a very good question. We need a few kilograms of, say, hydrogen and oxygen or deuterium and oxygen, which is basically fed into our heat engine, which we need anyway. That's what converts the waste heat into electric power to start the machine up. So if it did shut down, you could start it up fairly easily. In fact, we have a U.S. patent on the startup method for any kind of fusion reactor in space.
Okay, so it sounds like it's, like you said, a self-sustained net positive system.
Correct.
So okay, let's leave space aside for a second. I mean, that seems to be like the holy grail. So why is nobody kind of pursuing this for terrestrial power generation?
Well, that's a good question. Most people are interested in baseload power generation. So they want to contribute to, producing gigawatts of power. And that's where the big tokamak makes sense. For example, if ITER, then demo, then power are successful, you're going to have gigawatt fusion reactors, which will contribute major amounts of power to the grid. Our technology, because one, we're using helium-3, and because it's small, is really suitable for more niche applications. Like there are places in Alaska, for example, where they get their power by flying in diesel fuel in white planes. So it's incredibly expensive. So they would be a market for this. Anytime you need portable power, like, for example, oddly enough, in an oil rig, this would be an offshore oil rig. This would be a great application. So ours is smaller applications. As I mentioned earlier, there's enough helium production from natural gas mining and fracking and things like that to sustain about 1.5 gigawatts a year. That's a tiny fraction of the world's demand for electricity, but it meets the needs of a lot of people, like places in Africa where they don't have a grid. This would be really great for them too.
Okay, so gotcha. Smaller size, more expensive. I mean, and frankly, I promise we'll come back to space because it's called the Space Business Podcast after all. But the thing that now springs to my mind is, so the other use case where that would seem to make sense and where people are extremely price insensitive is to just use that in theaters of war. I mean, if I remember correctly, the main reason of KIA's killed in actions in Iraq was people guarding diesel transports for power generation.
That's absolutely correct. In fact, the U.S. military has a requirement that their brigade combat teams operate for 1 week without fuel supply. And you say, well, how are they going to do that, especially when they're electrifying the battlefield? And this would be ideal for it. Now, getting back to space, though, here's the interesting thing. If our technology is successful, and we're building transports for space, there's really nothing to stop you from going to the gas giants like Uranus or Neptune and taking helium-3 out of their atmospheres and bringing it back to Earth. Then indeed, you would have baseload power capabilities on Earth. And you might say, well, that's really fantastic. But I should mention my dad worked at Bechtel, and he was one of the engineers who went to Saudi Arabia in the 50s and started building up their oil industry. And, if you back in the 50s, you had said, hey, we're going to build super tankers and bring oil back from Saudi Arabia, people said, that's crazy. Come on, you're never going to do that. That's not practical. And that's what we do today. So the idea of extracting helium-3 from the atmospheres of the gas giants is quite plausible. There's an engineer at NASA Glenn who's written numerous papers on the technology needed to do that. And we recently published a paper on the economics of that. And it turns out that the levelized cost of electricity, even with fairly conservative numbers on what it would cost to build the infrastructure, are very competitive with any other terrestrial source, even wind and solar. So it's pretty exciting. And again, this is the cool thing about our technology. Yes, it lends itself to portable, high-value applications, which you mentioned on the Earth, but the space technology opens up whole new ways of powering the Earth. You can certainly go to the moon, but it turns out that going to the gas giants, if you have this technology, makes just as much sense and maybe more sense.
Having said that, though, I was going to ask you about the moon, right? Because hopefully it looks like that's where we're going back to now, right? We had Artemis 1 end of last year. There's actually a private company lander in lunar orbit as we speak, the Hakuto R lander, Japanese company, iSpace. There's a lot of other missions planned to the moon. There's people, actually the sort of last phase of the Artemis program does call for the establishment of a permanent lunar base, which obviously will also need power, right? And then if I remember correctly, and I'm no expert in sort of like lunar geology and composition, but I do seem to remember that because of the constant solar wind and there's no atmosphere, that there's quite a bit of helium-3 deposited on the moon, right?
That's correct. In fact, the Apollo astronauts brought back helium-3 in some of the lunar samples. So yes, it's quite possible. In fact, we went through a design of a lunar transport system which would land on the moon, bring helium-3 back to Earth, and then you would send the vehicle back. It's sort of reusable vehicle we developed exactly for that purpose. So yes, you absolutely can do that. You do have to have the mining infrastructure, but if you talk to the big companies like Schlumberger, and you said, oh, it's going to cost you 20-30 billion to build a lunar infrastructure, they go, yes, so we do that all the time. And it's incredibly expensive, and the scale is just unbelievable. But they're quite comfortable with it. Again, if there's a business case for it. In other words, if there's a helium-3 reactors that need it on the ground, they would build the infrastructure on the moon.
Yeah, terrestrial mines are very expensive.
Sure, absolutely. NASA has 3 contracts out for lunar fission, and those are really great, really interesting work. 3 different teams are working on it. We think that our technology would be superior to that. Although, again, we have to demonstrate the physics. One of the things we always want to be careful about is, and Chris can explain this in more detail, we still have to study the physics of the FRC in much more detail. There are maybe 200 operating tokamaks around the world. The Soviets started the work in the 1960s, so the physics is really well understood. And FRCs, there's 3 major efforts: ours, Helion, and TAE, which are all working on it and all doing great work. But we need to study it more to really demonstrate that this is a viable technology. You can't underestimate the challenges of anybody's fusion technology.
And then maybe Chris, can you take us through what is left to be done on the quote unquote physics side in a way that most of our listeners will be able to understand?
Sure. So it depends. There are things that depend on the different FRCs. As Mike mentioned, there are 3 main companies, at least in the US, that are working on field reverse configurations. There are also a few different universities throughout the world that are working on field reverse configurations. In terms of the actual tour de plant, it's the things of, let me see, sorry, just collecting my thoughts here. So demonstrating like high enough temperatures in order to get fusion relevant. FRCs normally work with the alternative fuels such as deuterium helium-3 or proton boron, and those have at least, let's say, 5 to 10 times more temperature requirement than the mainline fuel of deuterium tritium, which is going to be used in ITER and other reactors. So there's this higher temperature requirement that's important. The highest temperature a tokamak got in the world was this number around 60 kiloelectron volts, which is about 4 times greater than that needed for deuterium tritium. So it hasn't been. There's some glimmer of that kind of temperatures being achieved, but we need to achieve those in a field reverse configuration. So that's a very important part first. Next part is having high enough confinement times and demonstrating those, right? There's a lot of physics there of how, if you turn the plasma off, let's say, or you turn the heating off, how fast will the energy just leave, right? If the energy leaves really quickly, then you don't have a nice self-sustaining cycle that you can maintain and get a lot of energy out. So there's a lot of work that's being done there, and that also connects with things like instabilities. There are various types of ways that the plasma can, let's say, spin up in a way you don't want it to, or maybe tilt in a direction you don't want it to, that can lead into disruption of the plasma. And so there's been a lot of great work done so far on maintaining these instabilities. And we have some, from some theoretical estimates, we suspect that some of these will not be too much an issue for our FRC because they happen to be in a bit of a different regime of where it's something between the fluid and kinetic, where fluid is like the particles operate more like a fluid. They're kind of denser and and move as if you have like this magnetic fluid, while kinetic, usually the particles are a little bit more independent. And so they don't work as much like a bar magnet. So we're a bit more in that kinetic regime, and that may end up helping a lot in terms of stability. So it's a few things like that end up adding up to the types of challenges on the physics side. And then there are also some engineering challenges as you get to a full reactor.
Yeah, and we should mention is that, we currently are running PFRC2, which is an experiment where we're studying these things. And the next step would be PFRC3, which would be a machine with 10 times the magnetic field, 10 to 20 times the magnetic field, and be able to reach temperatures we would hope of 5 to 10 kiloelectron volts, where you actually could see some deuterium-deuterium fusion. And that machine would be used as a physics demonstrator. So it'd still be a plasma experiment. It would not be a power reactor, but it might also allow us to have long pulses of fusion to study a burning plasma, which is also important. One of the things that people have discussed is that nowhere in the world has anybody been able to study a burning plasma, where you get hot products, they have to be exhausted or they interact with the other ions. And that's another physics challenge that everybody's going to face. So we may begin seeing those in PFRC3. And that's like a 40, 50 million, maybe 5 to 6 year program. That would be the follow-on to PFRC2.
So right now you guys are on PRFC2, you mentioned?
That's correct.
Okay. And so you're saying, so if you had sufficient funding, 5 to 6 years from now, you may demonstrate the first fusion reactions.
That's correct. And that, again, that would be maybe 5 kilowatts of fusion for a couple hundred kilowatts of input power. So it would show that it works. Then the next machine, PFRC4, would be an actual power plant demonstrator. Mm-hmm. But also what we would hope to do in PFRC3 is to demonstrate things like the vacuum vessel. We have to have a very specific kind of vacuum vessel, ideally, and we don't know if we have to have zones which will allow RF to penetrate. Mm-hmm. So we want to put our antennas outside the vacuum vessel. And there's some work being done by other people on vacuum vessels which have such areas that are RF transparent. But we'd like to demonstrate all this in PFRC3, demonstrate shielding, demonstrate that we can protect our superconducting coils from the low neutron flux, and all these other things, and also high efficiency RF heating and really good plasma interaction. So the goal is that PFRC3 would be physics and engineering demonstration. So in PFRC4, we're ready to build something which would be a real prototype.
Yeah. And then since you've mentioned neutrons a few times now, and again, I'm no expert, but from little I remember sort of like neutrons are not necessarily good, especially fast neutrons are not good for materials or human beings and things like that. Sort of what is there any safety concerns around this? And so, for example, could your system ultimately, could it be used for crewed transport as well, or would it just be robotic?
We have to protect the superconducting coils from the neutrons. Now, the D-helium-3 reaction does not produce neutrons. It's aneutronic. However, you have deuterium, and deuterium is going to fuse with deuterium. Now, we do a lot of things to minimize that, but you get lower temperature neutrons than you would get in a DT machine, like we're 2.45 million electron volts, theirs are 14. So they're not as damaging and there's not as many, but you still need, shielding. And that's one of the things we want to study is how to build really effective shielding. Now, in a DT machine, the current thinking is their neutron shielding is also used for breeding tritium. And it's also part of the working fluid in their heat engine to produce electric power. We don't have to do any of that. So we have a simpler problem. So we can focus on optimizing the shielding. So yes, this could be used for human missions. It's actually, the neutron flux is much lower than that, say, of a fission machine, for example, which are also being considered for human experiments, human flight. Absolutely. I mean, typical, if you look at one of our models, we have our fusion engine at one end and people at the other end. So, and then all the fuel tanks are in between. So just the general, you're absolutely right in terms of general safety. You want to put the people as far away from the fusion plant as possible. That said, it doesn't take a lot of shielding to make this safe for people. And for example, we think a truck, a typical military type truck could handle a 1 megawatt electric machine with sufficient shielding to be safe to the people around it, to the operators.
Yeah. And I guess you could still try to put, I know that helps, you could put some distance between the propulsion unit and where the crew is as well.
That's correct.
Yeah. And then sort of on the space mission, space architecture side. So unless I'm mistaken, just to confirm, this is in-space propulsion, right? This is not suitable, doesn't have the thrust away to, like you can't get out of the Earth's gravity well with this.
We're producing, say, at an exhaust velocity of 100 to 200 kilometers per second, which makes you very fuel efficient. Okay. But we're producing 5 newtons of thrust. So there's basically power is proportional to the product of thrust and exhaust velocity. So the higher your exhaust velocity, as from the rocket equation, you get more payload per unit fuel.
Yeah.
But at the same time, if you have a given amount of power, you can trade it within sort of bounds. We can't drop our exhaust velocity to say 10 kilometers per second, or it doesn't work. So we're restricted to maybe 80 to 200 kilometers per second. But that's sort of ideal for solar system missions, and also pretty good for the next generation of interstellar missions that NASA and other people are talking about. Like one mission is to go to the 600 or 700 astronomical unit mark, where you can use the sun as a gravitational lens, and you'd be able to image extrasolar planets about as well as you can see the Earth from geo-orbit. So that's one application. And our technology is ideal for that, because not only do you get there, you can stop, which is ideal. And then you can maneuver, because you have to move the spacecraft a small angular distance to actually do the scanning of the extrasolar planet.
Yep.
And so, sorry, what was the exhaust velocity again you mentioned there for your system?
It's anywhere from 100 to 200 kilometers per second.
Wow. Okay. So that's, for memory, I think the best we ever achieved with chemical rockets was something like 5. So
that's right. And a Hall thruster gets about 20 kilometers per second.
So still like an order of magnitude better.
I mean, there are some electric thrusters that get close to 100 kilometers per second. I think there's a European one that gets 80.
Okay. So very high efficiency, low thrust, but sort of kind of, okay, perfect for in-space propulsion. Kind of in a way also means you get sort of, the farther away you go, the more sort of relative bang for the buck you get, right, over alternatives.
Right. I mean, it's really cool. Like NASA and other people are sending missions with solar cells to Jupiter, but the arrays are enormous. And that's kind of beyond Jupiter. It's impractical. So after that, you need to use RTGs, but radioisotope thermal generators are, 200 watt class. So how much can you do with that? Now, if you're familiar with the NASA Jupiter Icy Moon Orbiter mission, JIMO, that was 100 kilowatt electric. And they actually just plan all these really cool instruments that drew, you need a kilowatt here, a kilowatt there. And unfortunately, that mission was canceled because developing even a fission electric system was very challenging and extremely expensive. I believe the initial budget was $16 billion for that mission, and everybody figured it would grow to 30. We need up the whole NASA budget. So that is a real challenge for nuclear electric, which is why it's not being pursued in great depth now. Now NASA is interested in nuclear thermal, because that helps you a bit if you want to go to Mars with people. It shaves a couple of months off the trip.
Well, I was saying, NASA's interested in nuclear thermal again, right? Because they had been already at some point in time in the past.
Well, right. And NASA did build nuclear thermal rocket engines and tested them on the ground in the early 1970s, the NERVA program.
Yeah. Sometimes people forget that NASA did like a lot of these things back in, I guess, the 60s and 70s, right? Including crazy stuff with the nuclear thermal. Then there was I forget the name of the project, the crazy one, basically throwing out fission bombs to back.
Orion.
Yes.
They also had they invented the bumpy torus, which was essentially a bunch of mirror machines in a torus. And NASA was doing a lot of fusion work, but it all was canceled because, again, fusion is a long-term thing. For us, we think 10 to 15 years if the physics work out, as Chris was describing. So it is challenging, and it's hard for any organization to think in that kind of long-term process. Yeah. So that's one of the challenges when people are looking for something that flies in 3 years. It's not going to be our technology.
When, I know this is a difficult question. Assuming your funding is there for your various stages, when would you envision having a kind of prototype engine in space?
Well, that's what I'm saying. PFRC-4 would be close to a prototype engine. So that's maybe 10 years. But again, it really depends on, we have not procured funding for PFRC-3. We're still running experiments on PFRC-2, and we're learning a lot, and that's great. So we really need to go through the PFRC-3 phase, which again is to build it. It's about 2-3 years. And then we want to hire a whole bunch of physicists. We have to train people to work on FRCs, because most plasma physicists, and there are many great ones around the world, work on tokamaks. Some work on stellarators. So it takes time. As Chris was mentioning, the way this machine operates is quite different. So you have to learn the different physics. And that would be part of the PFRC-3 program. And then PFRC-4 would follow that. Again, it takes the machines are not that complicated. A Chinese company duplicated PFRC-2 in 6 months. They built a copy of it. So it's not hard to build it. Basically, the magnets are things you see in an MRI machine. The heat engine is what you see in a helicopter gas turbine engine, about the same size. So that's not the real challenging, but putting it all together, of course, is always a challenge. Just building anything is a challenge. Look at people, the problems they have with electric cars. They build them and then, oh my gosh, we got to recall them because it's problems we didn't anticipate. So all new engineering has going to have hiccups and going to have issues. And this will be no exception. But maybe 10 years, if we were given lots and lots of funding, we would build 2 PFRC-3s and have 2 teams of physicists working on it. So it really depends on the funding level. There was a really great chart that the Plasma Physics Lab produced years ago, and they showed progress in fusion as a whole is exactly proportional to the funding. As the funding goes up, they make progress. Plasmas get hotter, they can find them longer. They get longer, burning plasma pulses like they've been done at JET and at Tokamak Fusion Test Reactor here in Princeton. But then the funding goes down and the progress goes down. So now there's a lot of private money going in, which is great. TAE has a lot of money. CFS has a lot of money, and they're all going to make good progress. But again, if the spigot goes off, the progress stops. And it's, again, fusion is something which have to have a longer time horizon. And the time horizon for ITER, which is, they have some of the top plasma physicists and engineers in the world, is 20, 30, 40 years for the big tokamak like theirs. And maybe people at CFS or the various stellarator companies will be able to come up with a faster method, and that'd be great. But you're still talking about a lot of fundamental research that has to be done for everybody's machine. And then, of course, there's the engineering materials challenges. There's a lot of CFS and other people doing great work in high-temperature superconducting coils, which would help everybody, including us. We can get by with low-temperature coils, but high-temperature ones, if they were cost competitive, would make our life easier, too. So we're very excited about the work they're doing.
Yeah. So, I mean, I fully hear you. And, of course, my main job is having a VC fund, for example, the lifetime of our fund, our current fund, is the same as many other people's funds. It's basically 10 years, right? So typically you want to have an exit with 10 years, and that's anything that's a little bit too visionary. It becomes more complicated. Having said that, this does also seem like, fusion in general seems to be like a very strategic thing. So really, there should be government support for this. And you just mentioned China copying one of those, and that should be a great motivator for government funding.
It should be. One of the cool things about our technology, though, is, as Chris mentioned, it's RF driven. So because of that, we have to build power electronics. And because of our developing expertise in that, we were given a contract by ARPA-E to develop power electronics for the entire fusion industry. So that's what we're doing right now. So as we develop our PFRC technology, we're also developing products that we can sell now. In fact, we're talking to a couple of organizations about buying our power electronics to demonstrate in their machines, which are completely different from what we're doing, but they still have a need for RF power generation and for power electronics for neutral beam heating and things like that. So we actually have some nice products in the pipeline that we hope to start selling.
And that's always helpful. And so if I summarize this, from everything we talked about, it seems like on the R&D roadmap, you guys have a pretty clear roadmap. And yes, like you said, some of the physics still have to be proven, but there's a roadmap. And is there any obstacles on that roadmap that really worry you that just may really not work? Or is it something like if you put enough funding and work into it, it should happen?
There's always the potential that PFRC-3 will find something about the plasma which we can't solve the problem. It's not possible. We don't think there are. The theory says there shouldn't be. But again, you look at the history of plasma fusion, and all the advances have been through experiments, and they've been surprises. The stable modes that are used in tokamaks now were an experimental surprise. Like, what's happening? We don't understand. Oh my gosh, we've discovered a new mode where it's much more stable. So the plasmas are always going to surprise you. And that's why you need experiments. You can't sit there and do analysis and numerical simulation. Oh, we can guarantee we have an operating machine. I mean, that's true in basically all aspects of engineering. You can't design a car in CAD and say, okay, let's start selling it. You got to build it and they drive them around for 2 years to get all the bugs out. And everybody has that problem in real engineering in projects. So there's always going to be a potential for surprises. The theory and analysis we've done today say that we shouldn't have anything that we can't solve. But that's, again, what PFRC3 is all about. It's sort of in the scale of plasma research, it's a fairly modest investment to really make sure we understand the plasma physics well enough to build an operating machine.
Right, and I'll add to that we would be pushing the envelope on radio frequency driven FRCs, right? Usually these radio frequency ones using this thing called the rotating magnetic field have only gotten up to certain temperatures that weren't that high. And it's really with the innovation to the RMF rotating magnetic field that Sam Cohen introduced of something called odd parity. Essentially, you flip over a mirror, and on one side of the machine, the magnetic field is up, the other side it's down, and they rotate instead of all of them being up at one time. So that actually results in some really nice magnetic field properties where the field lines are much better closed and prevents particles from leaking out. So that's a very new technology. In fact, a very unique part of our system. And so with that, there's a lot of potential gains. Of the simulations seem to show some really promising results. And there's been some helpful initial results from the initial experiment runs that we've done. But there's also high risks because it is such a new type of technique. So that's what I would say.
Yeah, thank you. So as we're coming down towards the end of the podcast here, so the usual last question is that I ask is always about favorite science fiction, and if you guys want, we can do this. But I was going to ask you a slightly different question because I mean, you guys are clearly, you're working sort of on the very visionary end of space propulsion, and I understand that your specialties are, this is basically plasma physics, but you guys clearly know a lot about physics in general. Let's say we're 10 years down the road, 10, 15 years down the road, this works, and we're thinking about sort of the next thing after this, and just really, if we're dreaming, going crazy, stuff like Alcubierre, warp drive, that kind of thing. What do you guys see out there?
The interesting thing, as I mentioned earlier, we're kind of limited to 100 to 200 kilometers per second exhaust velocity. And that means that we've designed missions that go to the orbit around Alpha Centauri. That's a 500-year mission. To get there much faster, you need exhaust velocities more like 25,000 kilometers per second. And that would require the next step beyond what we're doing. We've thought a little bit about how you were doing, but that would be the next challenge. So the next challenge is to get a fusion rocket that can get to, say, 1/10 the speed of light or something like that. So you can get to Alpha Centauri in 50 years. And that would be the next big thing. Sure. We know that there are people at NASA who are exploring concepts of warp drives and things like that, but we're not involved in that kind of work. I mean, that's what everybody would love to have, right? We'd love to be able to go around the galaxy in starships, but nothing we're doing really relates to that. But the idea of, the next step for us would be a much higher exhaust velocity. That would be of great interest.
Is there anything you want to add on the really futuristic stuff?
Oh, no, I agree with Mike's statements there. I think, essentially enabling that break into interstellar travel, right? So, and that's, you do need to get to exhaust velocities that are much closer to the speed of light. And I mean, the nice thing with fusion products is that the products themselves actually do come out quite fast, right? They are around, let's say, 1/10 or so the speed of light when they leave the fusion reaction. So I think if there's a way to magnetically or some way cusp those and push them out a rocket very directly with such high speeds, I think that would be really the next iteration and next step. It'd be really exciting.
Cool. But in the meantime, what you guys are working on, that would already be fantastic progress. So, I think myself, and I suspect most people in the space community, are really crossing the fingers that we will have fusion device within 10 to 15 years. So, best of luck with that. And, thank you for taking the time today and explaining some of your work to our listeners.
Thank you very much. It's been great.
Thank you.
Well, that's it for another nominal episode of the Space Business Podcast. If you like this podcast, please consider giving it a 5-star rating on your favorite podcast platform, such as iTunes. You can follow us on Twitter at podcast_space. Also consider supporting us at www.patreon.com/spacebusinesspodcast. If the podcast got you interested in learning more about the business opportunities in the space economy, check out my new online course on space entrepreneurship on udemy.com. The link is in the episode description. Lastly, if you have any feedback, including ideas for guests, and that may include yourself if you have an exciting space story to tell, or interested in being a sponsor, drop us an email at spacebusinesspodcast@gmail.com. I look forward to seeing you for the next episode.